Style of an image refers to textures, brush strokes, and color distributions whose occurrences are dependent on each other. Capturing these styles from image and applying it on a content image to get the final image like this is what we call style transfer. In this video, we'll understand how style transfer works and how we can build one from scratch. Humans have developed some complex understanding of visual perception due to evolution, which gives us ability to create unique visual experiences through composing a complex interplay between content and style of an image. But we can't peek in our brain to see and understand how the scenes are being processed. That's why the algorithmic basis of this process is unknown. However, in the area of computer vision and deep learning, there are some models exist which performs near human when it comes to extracting information from image. Let's take VGG19 model to understand it better. VGG19 achieved state-of-the-art performance in image classification task, which is a deep convolutional feed-forward neural network. And its architecture is divided into two parts. The first part is deep convolutional neural network which extract features from images, and the other one is a normal feed-forward network that predicts the output and act as a classifier. So we are interested in this part right now because it extracts features from images. It means the whole network has some solid understanding of images. Each layer in the network learns different features, like in this scenario, the initial layer learns some low-level features like edges, curves, and when it starts going deeper, it starts learning some high-level features such as textures, objects, and distributions. And by learning these things from images over and over again, the network develops a complex understanding about images. So when you feed an image to it, the layer will store features in the form of feature matrices. Now we already know that the style is nothing but a correlation between shapes, color, distributions, etc. So we can trick the network to extract style from feature matrices, and the trick is known as the Gram matrix. Gram matrix is a style representation that computes the correlation between different feature matrices, which helps to capture the style of an image. I've already made a video about Gram matrix and how it captures style, which is essential for this video. I'm requesting you to watch that first. The link is in the description. Now we know the science of capturing styles. We just have to apply it on content image to get the final result. So the style transfer will be performed in following steps. The content image will get into the network and we will capture the feature from a little deeper convolutional layer of the network. This will give the complex feature of content image. In the same way, we'll push style image into the network, but at this time we'll capture feature from the first convolutional layer from every block. First layer, because it contains low level features of an image which we will need to get the style of an image. So we'll store the features from every layer for every block. Now the final step is to generate a white noise image and feed it into the network. Capture the features for content and style feature from their respective layers, and in this way we will have the generated output and the original output for both content and style. Now we need two loss functions, one which measures content loss and one which measures style loss, so that we can perform backpropagation on image to reduce the loss as much as possible. So the final loss function which we have to minimize is the summation of content and style loss. Now we got how style transfer works, but only explanation is not enough. The best way to learn and understand it by creating it from scratch. So let's implement and see how it works in code. This is my hardware and software specification for this tutorial, so make sure you have the same version of libraries to avoid any version. Start by writing a function to load the images into memory. Read the image file and then decode it as a JPG, where channels is equals to 3 represent RGB image. Now convert the pixel values to 32-bit float and get the shape of image. And from that, take the ratio to resize the image. Once you have the rescaling ratio, rescale the image and expand dimension by 1 before returning it. Then download the content and style image from link in the description to your working directory and define their paths to respective variables. Now make a function to plot images. If the image has more than 3 dimensions, then squeeze it into 3 dimensions, then plot it using IamShow function. If you want, you can put title in the visualization. Let's check both the function. First, load the content image and style image and check their shape to make sure that they are loaded properly. Now make a canvas to plot images. Plot the content image first at first subplot and the style image at the second subplot. Now we have a content image and style image loaded and ready. Now get the preprocess function for VGG19. Once it gets done, download the VGG19 model with the pre-trained ImageNet weights. And include top equals false represents that you are only downloading feature extraction part, not the classifier. Summary will show the layer of the model. And you can see that there are no dense layer at the bottom, neither the input layer at top. Now get the name of every layer so that we can take the output from desired layer. Now here you can see for every block there are multiple convolutional layers, but we want the feature output for style is from first convolutional layer of every block, and for content we can have feature output from second layer, but you can also experiment with third or fourth layer of the block. When you have done, store the number of layers for content and style. Now define a function to get the output from that layers only. So get the model first, and the training is not required for this process. Get the output layer from the model by using name of the layers. Finally, attach those layers to model's input and return it. Now use the above function to extract and store feature for style layers and feed the image to it. And we can verify the output by checking shape from every layer. So this part is the dimension of feature matrix and this is the number of feature matrix. Similarly, we can get statistics for each layer and input for both style and for content. Now write a function to calculate gram matrix. The equation is implemented by using Einstein's summation notation. Once it's done, get the shape of the tensor, multiply them together and divide the result to get the gram matrix for that particular layer. Now use the model to get the output. Attach the output layer to the model and set style layer and content layer instance. Get the length of style layer and set the trainable parameters is equals to false. Now write the flow for model. First, denormalize the value and feed it into predefined VGG preprocessor to process the data and get the output from layers. Now slice out the output from style layer and content layer separately. Calculate the gram matrix for output from each layer. Now store the output from each layer in the dictionary with the keys as layer name for both content and style layers. At last, store both the dictionaries in another dictionary for easy accessibility. Let's test the above workflow. Load the style content model class with both style and content layer and feed the content image in the model to get the output. We can verify it by iterating through outputs from each layer and get the statistics. And here's the output from all 5 layers in the form of feature matrices. Also, we can verify the output for content by doing the same. The feature matrices are the target feature for the content and style which we have to achieve from the noise. You can also visualize the feature from particular layer like this. Now take the content image as noise image because the noise image will take more time to converge and the content image is already close to the content feature target. So the model has to focus on minimizing the style loss more, which will lead to faster convergence. This function is normalizing the image at runtime. Choose the optimizer to optimize the error and define the weight for both style and content for best balance in final image. These values are taken from paper. Now define the loss function. First, get the output for both content and style. And for style loss, we'll implement mean squared error between output from noise and target output for output from every layer. Similarly, do the same for content output as well. And finally, add both the style and content loss to complete the final loss equation. Now write the train function to iteratively minimize the error. First, get the output for noise, image, and then measure the loss using above made loss function. Now use the gradient tape to measure the gradients and then use the optimizer to backpropagate error to reduce the loss and normalize the image for next iteration. When it's done, run it for some iteration to see the sample. Let's write a function to visualize output. First, denormalize the image and convert it into NumPy array. Make sure to select the first element from the tensor to get the image and return image from array. Now run the training step for 10 epoch with 100 steps per epoch, and for every epoch and for every step for that epoch, run the train step function. Clear the current visualization from notebook and display the newly generated image from the tensor. Now you can see how the style is blending in this image. When it's done, you can directly compare it with the content image to see the difference. So here's the final image, and this was the tutorial for style transfer. So now here are the 3 things you can remember from this video. Convolutional neural networks develop some complex understanding in form of feature matrices. Getting the style from those feature matrices directly is not possible. That's why Gram matrix is used to capture the styles. This method of style transfer is faster than any other training method because we are not training the model to do the style transfer. This was a basic intro to style transfer, but there are some more techniques that perform extraordinary style transfer. But that's the story for another video. So thanks for watching.